Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. My goal here is to find the top people in their profession, the 1 in 1,000 person that really goes above and beyond a typical practitioner. So I think I've got one today. It's Professor Gerald H. Pollack. He's also an author. He's at University of Washington, Department of Bioengineering. I saw a talk he did on what he calls the fourth phase of water. He also has a book on it. So I want to talk to him about that today and welcome him. Jerry, thank you. How you doing?
I'm doing great. Thank you. It's a pleasure to be with you and looking forward to the interview.
Oh, good. Yeah. So what was your first brush with the sense or the idea or the experimental result that water was not all that it appeared to be?
It started with Gilbert Ling, who unfortunately passed only a few months ago, just shy of his 100th birthday. And Gilbert had written, the time I met him, 5 or 6 books. And the major theme of those books had to do with water. And the idea was that inside the cell, the water molecules were not like water in a glass. The water molecules were lined up like soldiers at attention. And this caught my interest. It was my first brush, you might say, with a water that might be different from the ordinary liquid water that we think about.
Okay, and from there, where did you go?
Well, okay, so from there, I showed one of his books. I met him at a conference in Hungary, in Budapest, and after that, I got one of his books. I had already read that book and gave it to my students and postdocs to read. And every one of them came back to me and said, this is really important stuff. This is so important. I'm not sure that he's exactly right on everything that he professes, but the general concept that water in biology differs from ordinary water is really compelling. And so I took it upon myself to write a book. It is not the book to which you just referred, but to write a book that dealt with Gilbert Ling's ideas of water inside the cell. And my book, 2001, is called Cells, Gels, and the Engines of Life. And the goal of that, sorry?
Oh, yeah. What I want to ask you, about your book, but what are the ideas of Gilbert's that really captured your attention? What is it about water in regards to biology that is different about it?
Well, if Gilbert was right, and now I'm absolutely convinced that he's right based on our own experiments, that if water inside your body is different from water in a glass, most of us think that water is water. It's just H2O. And that's definitely not true from the evidence in Gilbert's work and our own evidence and many other people now as well. Then all bets are off if you try to interpret anything biological with the presumption that the water that's inside the cell is like ordinary water through which all substances can easily diffuse. And it's not that way, then everything that's based on that concept needs to be revised. And I am absolutely convinced that the textbook needs to be revised because Gilbert Ling's ideas and also other people before Gilbert and our own work is suggesting that the water inside the cell is very different and that it's actually the transition that occurs between this ordered water, whose structure we think is different from what Gilbert Ling suggested, but it's another story. If this water, the water undergoes a transition between this kind of structured or ordered water, we call it EZ for Exclusion Zone water, is really there. It's the transition between that and ordinary water that triggers many of the triggers and participates in essentially all of the most important reactions that go on inside one's cells. So it's critically important. The distinction between the two needs to be made. So that's that. In a nutshell, that's where we stand right now. I
So
think.
What's some experimentation that you've seen or done yourself that you were like, what the? And you saw this fourth phase of water, this easy water.
Well, good question. Yeah. So based on Gilbert Ling's work, we knew that if the water molecules are ordered, it forms something like a crystal, this ordered array of molecules. And crystals, sort of like ice, for example, crystals exclude all kinds of substances. So when water freezes into ice, for example, it pushes out all of the foreign substances, and then you get a pure crystal of ice. Otherwise, it wouldn't be a pure crystal. So that's what these ordered arrays of water molecules do. They push out everything. So we were looking for an experimental preparation where it appeared that everything, or at least some things, were excluded, and we found it. And that was a critical observation, because we suspected and then proved that this region is a region where the water molecules are not free to bounce around a gazillion times per second, which is what happens in ordinary water. These molecules were ordered, and therefore they excluded. And what we looked at to begin with was tiny little spheres called microspheres. We put them in the water, and we put a gel inside the water, and we found that within a few minutes, the region right next to the surface of the gel pushed out the microspheres and then became devoid of these little spheres. And we suspected that this would be a region where the molecules were ordered, just as Gilbert Ling suggested, inside the cell. And we found indeed that was the case. We carried out a dozen different physical chemical experiments, and every one of them showed that the water in this zone of exclusion, that's why we call it the exclusion zone or exclusion zone water, that every feature that we investigated of this kind of water differed from features of ordinary water. So clearly this was distinct from ordinary water. And
quick question here about the exclusions. Have you videoed the exclusion happening? And if so, do the particles that get excluded, do they follow a certain path, or does it look random how they're excluded?
It's not exactly random. It builds layer by layer. So if you can imagine a gel or some other material, it doesn't need to be a gel, as long as the material is so-called hydrophilic, which is water-loving. It means that if you were to drop a droplet of water on a horizontal surface, it would spread out. So any of those conditions, if you put water that contains particles of any sort or molecules, what happens is the exclusion zone grows layer by layer. So first it's very small on a molecular scale, and you keep recruiting more and more layers of this kind of ordered water, and therefore the amount of exclusion progressively increases. And the excluded molecules appear beyond the boundary of this easy water. And once they get there, we don't exactly track them, but they seem to disperse seemingly almost randomly to regions beyond the exclusion zone. See, we haven't tracked them exactly because that's not critically interesting for us. What's more interesting is the exclusion zone itself, which contains the ordered molecules, which build layer by layer. What's interesting, because this region, which as I think I didn't mention, we call it fourth phase water, because it's not the same as a liquid or a solid or a vapor. It's the consistency is something like honey. It's a high viscosity, and the molecules inside of it are ordered. So there are more properties that make it even more interesting. You didn't ask me, but let me just
we'll get into it in a second.
Okay.
The
Sure.
reason I asked you about the exclusion process is, let's say you had fluorescently tagged molecules and you had this exclusion process go on. If you observe their paths of exit, where they aggregate, how they aggregate, etc., maybe that would give you an idea as to, what is doing the ordering. Why is the water doing this? That's why I asked.
Since it's a good question, but I think technical issues will limit the ability to see what actually is going on, because each of these molecular layers is on the order of a third of a nanometer, and the microscope can't resolve anything near that. And so it'd be really difficult to follow exactly what the path of exclusion of each of those particles or molecules might be. It would be great if we could. That would tell us a lot, as you're suggesting, but we can't do it as of today.
Okay.
Maybe next century.
So what is doing the ordering?
Well, the energy, I'll put it this way, the energy comes from light. We did experiments to demonstrate that. So if you have an experimental chamber with, let's say, a gel or a hydrophilic material, and you add water and particles to it, and the particles are thoroughly mixed to begin with, at first you see the particles right up adjacent to the surface of the gel or material, and gradually the exclusion zone builds. You see, sorry, the question you asked again, I think I got lost in my explanation. The energy. I was.
It's okay. I'll repeat. What is doing the ordering? As you say, is it just thermodynamic, or is it energy preferential forces? It's a lower energy state, or
it may be a lower energy state, but it requires energy to get there. Any kind of ordering thermodynamically requires input of energy, because nature tends toward disorder. So if you want to go from disorder, ordinary water, to order, easy or fourth phase water, you have to add energy. So we did experiments to figure out where the energy came from. And at first we had no clue. And finally, the answer turned out to be really simple: light. And particular wavelengths of light, we found that infrared wavelengths, that is beyond red, longer wavelengths, especially 3 micrometer wavelength, which is well beyond red, is infrared. And infrared is all around us all the time. It's almost impossible to get rid of it. Infrared light is what is more powerful than anything we looked at any other wavelengths of light, visible light, UV light, by almost 1,000 times. So you just add infrared light, which you can get from the sun or from virtually anything around you is generating infrared light. So when it reaches the chamber, it's that infrared light that creates the ordering, that builds the ordered exclusion zone, or EZ. And it does it layer by layer. That's what we found. So you add more infrared light using an external source, and the exclusion zone gets bigger. And you take it away, and it gets smaller. It's a very simple observation. So we know that the conversion from ordinary water to EZ water requires energy, and the energy comes from light, particularly infrared light.
So in sunlight, what's the infrared component, and does it change diurnally? Does that tell you how biology interacts with sunlight in yet a new way?
Yeah,
in our skin, it's the infrared component is it interacting with our cells in this way?
Absolutely. So everybody knows that plants get their energy from light, and the system is known to almost everybody's photosynthesis. Step one in photosynthesis is when light hits the plant. Step one is through a number of processes. Step one is the breakup of water into its negative and positive components. This is exactly what we found, but not necessarily in a plant. It can occur in a plant, but it also occurs outside the plant. In the plant, typically, the light is thought to be absorbed by the chlorophyll, And the water that's next to it is somehow, it's not clear how in this process, but somehow the water molecules break up. And this is the first step out of 20 or so steps. And this is exactly what we found. We found that instead of chlorophyll, we have virtually any, not any, hydrophilic surface. And in order to build this EZ, what happens, we deduced from various experiments, is that the water molecule breaks up into OH minus and H plus, just like the first step of photosynthesis. And then the EZ builds, and a whole story follows from this. The EZ is, in fact, typically negatively charged, like it builds from the OH minuses, and the H plus goes into the ordinary water. So this separation of charge that's brought about by light is very similar to the first step in photosynthesis. This first step is what's critical for building the EZ water. It's those OH minuses that gather together to form the EZ. And so light is critical, and the breakup of water into the negative and positive components is equally critical. And that's the step that leads to what looks like the first step in photosynthesis, except it's more general than what occurs in photosynthesis. It doesn't have to be a chloroplast or chlorophyll. Does that help?
Yeah, it's going to take me a little bit to unpack what you're saying here, but okay.
Monitoring itself, how are the water molecules oriented? Is it like in chains that, are they only oriented in one direction? Are they, in a 2D manner? How is the...
Yeah, so the water molecules actually undergo a change. It's no longer water molecules per se. The water molecules are broken up into OH minus and H plus, and the H plus, the OH minuses organize themselves into a hexagonal lattice, a sheet-like lattice. So that gives you the first sheet. And the second sheet is the same as the first sheet, and the third sheet is the second, and so on. So these identical sheets build, but the sheets are not exactly a collection of water molecules. They're a collection of OH minuses. And so, in effect, it's a chemical change that has occurred. And the chemical formula of what's in the exclusion zone is H3O2. It's not H2O any longer. And as I said, this is the stuff that's built with the energy from light. And the sun itself contains 50% roughly of sunlight is in the infrared range. So you've got plenty of infrared energy that's coming from the sun. That's what's required.
How does the wavelength of the infrared energy from the sun vary diurnally? And what do you think is the consequence of this? As a person, I wake up, I'm exposed to sun. The early morning light has some component of infrared energy that's in the right wavelength. And as the day goes on, that probably changes. And then evening, this influence upon my cells, at least my skin cells, changes. And then as I go into evening, that influence probably goes away.
Well,
so have you looked at that yet, or?
Yeah, it should certainly be that way, except the environment itself, not just the sun. Most of us don't go out in the sun a whole lot. Perhaps you do, but most of us don't. But even I'm sitting in my office right now, and inside of my office, if I were to shut the shades covering the windows, and it was so dark that I couldn't see anything with my eyes, or my camera couldn't record anything. If I were to whip out my infrared camera that contains a sensor, and the sensor is sensitive not to the visible wavelengths, which ordinarily characterize a typical camera, but only to infrared wavelengths, I get a beautiful image of everything in my office because everything is generating infrared. So it means that when you're sleeping, the infrared energy that's coming from your bed, from the walls, from the pictures on your walls, et cetera, you're still getting that. And so in theory, this should continue to build easy water. You might have more of it during the daytime when perhaps it heats up a little bit more inside your room. On the other hand, if you spend your life outside, still there's infrared energy coming from all the plants and such around you. So even though the sun is not shining, the diurnal variation that you're talking about, still you're receiving some infrared energy. And if you receive no infrared energy, which means you're at 0 degrees Kelvin, it's hard to survive at a temperature like that. But that's the only situation in which infrared energy is absent. See, so it's always there, and it's always feeding you, whether you're outside or inside. But presumably there is some diurnal variation.
I ask because, since this affects the water inside cells, that could be an explanation for a lot of mechanisms inside the body that, we had to attribute to something else, like the infrared saunas and red light therapy and things like that, and laser therapy. This is probably a hidden thing that's been going on that no one really is aware of.
Well, some people are aware of, because I talk about it all the time on podcasts and such, and it's in my book, The Fourth Phase of Water. Of course, if you go to a source of infrared energy, like a sauna, for example, you feel good when you come out. Most people feel really good. So if you have a muscle ache, often the muscle ache has disappeared. If you have a headache has disappeared. If you're low on energy, you feel more energized. And a logical outcome of the kinds of things I've been talking about is, every cell needs its complement of EZ water in order to function properly. And if you don't have enough of it, you're so-called dehydrated and you're not functioning up to par. But if you expose your cells to infrared energy, as from a sauna, then that's going to build EZ water and you're going to feel better. And so I think this is, as you say, it's sort of hidden from most people who are not familiar with this line of thinking, but it follows directly from this line of thinking that any source of infrared energy should be good for health. And I know a lot of people, even some physicians, who are not aware. I ran into one doctor in Germany once who was telling me that he treats cancer with infrared energy. Young women who have some cancerous growths on their faces, they don't want surgery. And so he treats them with infrared energy, and he said it's miraculous. The cancer goes away. And, so there are many health or medical applications of this EZ water phenomenon. If you understand that the cells are full of EZ water and that you need a full complement of EZ water in every cell to function properly, then the therapy becomes obvious. Since infrared energy builds EZ water, infrared energy should be good for health. And indeed, many people have shown that it is. So this is one of multiple promising therapeutic approaches that would really not have come to light had the phenomenon of EZ water not been identified or discovered.
What experimentation has been done to see what happens to a cell or an organism under the when it's in an EZ water creating state? Can you look at an individual cell and somehow glean that it's doing something different?
You can tell. One way of telling is by looking at the refractive index. So if the molecules are all aligned, the refractive index tends to increase. And there is a Russian scientist whose name escapes me. He has several papers that he produced showing that healthy cells have a higher refractive index than non-healthy cells. I'm sorry, I can't remember his name. That's one experiment. Another one is measuring the electrical potential of cells. So if the cell is filled with this kind of water, which has negative charge, you'd expect that cells that have a lot of this water should have a big negative charge, and cells that don't have much of it should have a smaller negative charge. People have measured the electrical potential of cells in healthy and pathological conditions. And the two studies that I remember, one is cancer cells, and instead of having an electrical potential, normal cells of minus 60 or minus 70 or minus 80 millivolts, their electrical potential is only minus 15 or so millivolts. And the same thing with pathological kidney cells. These are mostly old studies. People are not doing these kinds of studies because it has not seemed so interesting, but I think it's compellingly interesting. Pathological kidney cells also have electrical potential of -10, -20, instead of -60, 70, or 80 millivolts. So it's pretty clear that pathological cells have a lower electrical potential. And just a slight digression, those of your listeners who have studied physiology will know that the prevailing view about the electrical potential of the cell has something to do with pumps and channels in the membrane. And I've written several pieces attempting to dispel that notion. I think it's not correct for various reasons. And the correct understanding is that because the easy water that fills the cell itself is negatively charged, and the cell must be negatively charged. And the magnitude of that negative charge should depend on how much easy water there is in the cell. So pathological cells fail, not much negative charge. Normal cells pass the test. They've got a lot of negative charge. And so, it turns out if you build easy water, coming back to a situation that's normal, then the electrical potential becomes closer to normal. So these are just a couple of pathways that we and others have been pursuing to demonstrate that not only is the easy water critical, but there are ways of building easy water inside the cell and ways that can make you healthy. We tried, by the way. Go ahead, please.
Can easy water be made in a lab? Just you're hitting water with the right frequency of infrared energy and it creating an exclusion zone, or it only happens inside of the biological system?
No, that we do it. Most of our experiments are done in the laboratory, but it's really easy to do it. We demonstrated in a paper and also in the book that's called The Fourth Phase of Water, which has become popular, by the way. We demonstrated many times that you just put an infrared lamp near the water, and it's weak enough that it doesn't heat the water appreciably, but the exclusion zone grows markedly. So with a very, very weak LED source, light-emitting diode of infrared, we could build the easy. We've seen it grow by 10 times. It's very powerful. So you can do that. However, I think the question that you asked is really more: can you isolate this stuff and use it for something? And it's been demonstrated by an Italian group that they're able to produce easy water in solid form at room temperature. Think of it, solid water at room temperature. It's like a powder, and they've published several papers on it. The name is Vittorio Elia, E-L-I-A. And recently we tried to duplicate their result, trying in some ways to improve the technology of how they're doing it. And we were able to confirm that we can do the same thing they can do. And therefore, in the future, it should be possible to obtain this stuff. And you can obtain it, as I said, I have to laugh when I say it, because nobody could imagine solid water of some sort, easy water, at room temperature. You can certainly...
But is it maintained once you create the easy water?
Absolutely.
So it's not fragile?
Indefinitely. We have the powder that we produce, and we can keep that powder for months, and it's still the same as it was at the beginning. So if easy water turns out to be useful for anything, and we certainly have some ideas about how it could be useful, mostly for health, but other applications, this is step one, and I think it has a great future.
A little bit more about the structure of the easy water. You said it was like hexagonal hydroxyl ions that are loosely bonded together, and what about the proton component?
I'm sorry.
What about
the protons are beyond. Yeah. Well, yeah. So
the protons are what? Just, how are they structured? Are they?
Well,
are they bonded to the edges of the hexagonal?
Well, they latch on to water molecules and they form the so-called hydronium ions. That's H3O plus. And these hydronium ions are floating around in the water, in not the easy water, in all the water that's outside the easy. So it forms a kind of battery. And these are randomly distributed as far as we've been able to determine. That is, hydronium ions are randomly distributed. So you have, as I said, it's like a battery where the EZ is negatively charged and all those hydronium ions are positively charged. And the negative terminal of that battery is concentrated because the EZ is very tightly packed. It's one of the reasons why almost everything is excluded. Whereas the protons or hydronium ions are floating around freely and they want to distance themselves from one another because they repel one another. And some of those evaporate also. That's the reason why the atmosphere contains positive charge. This is well known and recognized, but nobody really understands where the positive charge comes from. And I think it comes from this very phenomenon of water being converted to easy water, those layers that build on one another, having negative charge, and the positive charge being released to somewhere, and much of it is going to be released to the atmosphere.
So what governs the thickness of the easy water layer, and can you modulate it?
Yeah.
What percentage of the given water becomes easy water?
Yeah. The thickness is a good question. Let me come back to that in a moment, but in terms of modulation, there are two things that we know. One is more infrared light gets bigger, and the second is number of protons. So when the proton concentration beyond the EZ grows too big, EZ can't grow anymore. We deduce this from a series of experiments. So that's what tends to limit the growth. EZ itself, the EZ grows layer by layer, and so the parts of the water molecules are laid down one by one, forming a sheet, and then the next sheet. The basis for the next sheet to grow is the first sheet. So the OH molecules seat themselves on the first layer, and many OH minuses seat themselves until you begin to get a full layer. And once the layer is full, then the next one builds in the same way. So each one of these layers builds on the previous layer. And so they keep growing until limited by, number one, the amount of infrared light that's available to break up the water molecules into OH minus and H plus so that the molecules can build, and also the number of protons or hydronium ions that exist beyond the EZ. That will be the limiting factor.
Okay. What you said it acts as a battery. How much energy could it impart? And have you ever tried to hook it up and use it as a battery and deplete its stored energy?
We have. One of my students did this as a PhD project, and his demonstration, again, this appears in the book, his demonstration was basically to put together a number of little cells, which had, he wasn't a gel, he used a hydrophilic surface called Nafion. You could use many things, water next to it, and he had two electrodes that are implanted in each cell. One that was immersed in the EZ and the other immersed in the region beyond. So you have one electrode in minus and one electrode in plus. And he hooked this up to an LED. And if he turned the switch so that the connection was made, that the LED would light up. And flip the switch the other way, would go blank, and so on. I don't remember, he tried to determine how long this could operate before it petered out. I don't remember the result, but in the particular configuration, I kind of remember it was hours before it began to peter out. There are various reasons, technological reasons why it could peter out. But, at least in theory, this has a lot of promise. And we formed a startup company called Fourth Phase Incorporated, where we're trying to develop not only this, but other applications of the fundamental science that I've been talking about. Another one is filtration. You don't need a physical filter because all you need to do is collect the easy water. As I mentioned, the easy water is devoid of all kinds of solutes, including junk and bacteria and whatever. So if you're able to collect it, you have pathogen-free water. And also, we think we can separate salt this way from ocean water, and we've started doing that. So development is limited by the amount of investment. And of course, like most startups, we're looking for additional investment to accelerate the process. We're very excited about these developments.
So where are you taking the research from here? Are you looking for commercial applications, or is that going to be left to others and you're still doing more of the fundamental studying of the structure and the effects of the easy water?
Well, we're in the laboratory, we're studying the fundamentals because that's so intriguing, and that, since you don't know what you don't know, there's a lot to know that we still are trying to find out. And we're working on that. The startup company, is working pretty much on the commercialization. It's not that we have great interest in the word commercialization sounds like money, and it's not that we have a great interest in making money. We think, given the state of the world today, the declining world, we're interested in contributing in a meaningful way to producing technologies that can solve some of the problems. And as you know, one of the main problems is water. There's insufficient water, and the quest for water supplies is getting increasingly shall we say, it's given rise to wars, and this is going to increase because water is a precious commodity. So if, for example, you can get drinking water, clean drinking water from ocean water, this would be a breakthrough. I mean, you can do it right now using reverse osmosis, but the cost of the energy that's required for reverse osmosis is astronomical, and people are using it, but it's easy for countries like Saudi Arabia or other Middle Eastern countries where oil-based energy supply is quite abundant, so they can do it, and that's where they get most of their water. But in other places around the world, and especially poorer places, if that kind of energy is required to produce drinking water, it's pretty costly and maybe out of the range of many. So in the system we're talking about, which is just a matter of collecting easy water and figuring out how to do this in a technologically straightforward way, this would be a real breakthrough, and we're hopefully continuing along this line. But as I said, limited somewhat by the amount of investment. So it still will require some basic science, which is done in our laboratory, and some development, which is done in the company. But we're excited by the prospect, and the only energy that's required is energy from the sun, nothing more. So
have you tried to impart very high intensity infrared onto water to create a large or significantly larger exclusion zone? Like, have you been able to grow one that's an inch wide, for instance?
It's an interesting suggestion. We actually have been thinking about that, but we're trying to keep it for the present time as simple as possible. Once you start adding light, if you're adding artificial light, that requires energy. And we're trying to do this in an energy-free way. But it's a good suggestion, and we have been considering that possibility for the future. There are some technical reasons why it's a little bit difficult to implement, but it's certainly possible. So thank you for the suggestion.
Have you tried to place, I don't even know, because again, it's so small, but if you had a bigger exclusion zone, what if you were able to place individual molecules into the exclusion zone and maybe try to do chemistry on them when they're in that zone, see if they're stuck or if they migrate once they're in there?
It's hard to do it if they're stuck. Almost certainly molecules and cells, for example, bacterial cells, almost certainly have exclusion zones around them, since the surface of the cell is hydrophilic. They have exclusion zones, but so it may be the natural state for such cells. But we haven't done any such experiments. Like the startup company, we're also limited by the amount of money that we have, because experiments require personnel, and the personnel require sustenance, and so somebody needs to pay them. And we're fortunate in having some people who believe in our experiments and such, and who are supporting us nicely. But starting to do biological experiments in a really meaningful way is another undertaking altogether. Early in my career, we did many biological experiments, but experiments are easier, in fact, if they're non-biological, because you don't have to worry about the viability of the cells. But this is an area that we probably will move into in the future, because it's so promising. Thanks for the suggestion.
No, that's fine. What do you think? So I know that cells have a lipid bilayer, but the interior of the cell wall, is that hydrophilic? And you're saying the exterior of a cell membrane is also hydrophilic?
Yeah. So the way the membrane is formed, it's a bilayer, and a lipid part, the hydrophobic part, is right in the middle of the membrane, the outer edges of the membrane, both facing the inside the cell and facing outside the cell. They're both hydrophilic. And so it's easy to imagine that EZ water would grow next to those surfaces.
But wouldn't that mean if they're setting up exclusion zones, I mean, substances would have to migrate through the exclusion zones unless the structure or geometry of the exclusion zone had a pore structure, let's say, to allow selectively things to enter or leave it or pass through it, right?
Well, I think that's the case. The evidence is, while we tend to think of the lipid bilayer, the membrane, as impermeable to everything, the question is whether it's really continuous or not. And typically biologists will look at the cell as having a continuous bilayer surrounding it, and the only substances that can get through are those substances that go through certain channels. And I think that idea is not correct, and maybe it's too much to go into here, but I've written some papers, and in my couple of books that I mentioned, this is discussed. It seems like heresy to suggest that the lipid bilayer is not complete around the cell, but experiments show that if you punch a hole in the cell, the membrane doesn't regrow, and yet the cell is able to maintain all of its function major function for a goodly amount of time. So it's not like you puncture a balloon and everything suddenly collapses. It doesn't work that way. Also, there are other experiments that show if you take a cell and you put some genetic information outside the cell, and then electrically you punch holes in the cell membrane, those holes, the material, if you punch the holes and you put the new material outside one day after you punch the holes, the new material can still get in the cell. And the evidence for that is the cell starts building proteins based on the new genetic information. So it must somehow have gotten into the cell even one day after the holes are punched in the membrane, which means that if you punch holes in the membrane, the cell will still live. It's no problem. And the implication of that is that the cell membrane itself may not necessarily be a complete enveloping bilayer that surrounds the cell. And as I said, I've written more on this in the two books that have been mentioned. So there are many things in biology that have been in the textbooks for one or two, even three generations. And we have a tendency to think that they must be true because they're in the textbooks. And there is evidence, if you are willing to look at it and take seriously, that suggests that some of these ideas are dead wrong. But the textbooks go on, and maintain the traditional picture. And one reason is that if you want to sell textbooks, you can't put radical ideas in because the universities won't buy them, and the publisher therefore doesn't want to publish it. And so it makes for basically a blockade against fresh ideas in the textbooks. And so the students learn the same thing generation after generation. Nothing changes, and yet the evidence can be starkly against the prevailing view. And that's
true.
Yeah, well, it's life, isn't it?
Just a couple more quick questions. I know we're getting to the end of the time. Have you been able to study some of the properties of the easy layer? Its surface tension, compressive or tensile strength, viscosity, etc. I think you said the viscosity is markedly higher.
Viscosity is higher. We've looked at birefringence, that is a measure of the alignment of molecules. We've looked at the effective temperature. We've looked at the electrical potential distribution over the entire EZ from where it starts nucleating until the end of the EZ. We've studied what substances get into it. Long list, and again, these are discussed in the book and all presented in the book as of 2013.
Okay,
when the
so
book was published.
For listeners that are curious about this, what's the book that they should get to learn more and go from here?
Well, there are two of them, and I guess the first one that I would do it in reverse chronological order. I think the one that has proved wildly popular is The Fourth Phase of Water, and it's like everything else on Amazon, and it's cheap. We designed it despite the beautiful illustrations done by my son, the artist, and diagrams and such. We wanted to make it accessible to the public, and so it's written for the layperson. That's the first one, and the second one, the one that goes before it, which I think although it's called Cells, Gels, and the Engines of Life, and although the book is now approaching 2 decades old, most of the material in there still applies. The nature of the structure of the water has changed since our experimental forays into looking into water. I talked to you about the layered structure. We didn't understand that at the time that Cells, Gels, and the Engines of Life was written. So a few things need to be revised a bit, but the essence of the book, I think, is still pertinent and correct. So those are the two that I would recommend.
Okay, well, very good. Well, Jerry, it's very interesting. I guess I was going to say at the beginning, I'm sure you've been attacked quite a bit because, your work is different, and I'm sure that's not, again, a lot of people embrace it, but I'm sure many more, unfortunately, because it's foreign, they attack it. But yeah, you can still continue, so that's good. So I appreciate you being on the podcast and coming.
Yeah, just a word about that. I'm actually surprised at how many have accepted it. I didn't expect that to happen because I've had enough experience in the past. In a former life, I studied muscle contraction, and I know the story about fresh ideas. On the other hand, there have been so many positive remarks. If you just look at the reviews of the Fourth Phase book, you can get some idea of what readers are thinking. The ones who are open to actually looking at the material, looking at the book and reading through, the response is really gratifying. I think we're onto something really important. And naturally, like others in the past, when you propose something controversial, there are many people who simply don't want to pay attention to it. It was Albert St. Georgi who won the Nobel Prize in 50, 60 years ago, discovering vitamin C, and who then studied muscles and cancer and all kinds of things, a real luminary. He said it was only when the response to an idea of his was polarized, in other words, only when he got strongly negative and strongly positive responses that he knew he was onto something really important. And so I guess one could say, you know, you look with pleasure on the strength of the opinions on both sides. And if they're really polarized, if St. George is correct, and he's correct on a lot of things, that's a good sign. When you have a lot of negative, when people are kicking and screaming and squawking, and other people are saying, yeah, this is just what we've been looking for. So I feel really good about that. So I hope that helps.
That's great. That's a good insight. And I'm glad that you feel that way.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.